Okay, this video is on trends in ionic size or ionic radius. And this really isn't so much a trend as in like earlier when we were drawing the arrows across the table for Zeph and atomic size. This is more of kind of a bold statement relating the sizes of cations and anions to their neutral parent atom. Okay, so the first thing we're going to talk about is cations. And so my first example is sodium versus the sodium cation. So there's a couple ways you can think about this. And so, of course, the idea here is who's bigger, who's smaller, right, in terms of size. So with this example, the easiest thing to think about is energy level. So remember that is always the predominating factor, is the energy level of the valence electron. So if we think about Sodium's one valence electron is in the N equals 3 level, and that's a 3s electron. However, when sodium becomes the ion, it loses that 3s electron, and then sodium plus's valence level becomes the N equals 2 level. Because sodium plus now only has valence electrons in N equals 2, it is naturally going to be smaller than the neutral sodium atom because it's closer to the energy levels are closer to the nucleus. So this is a pretty simple case where because the energy level has changed, the cation here is smaller than the parent neutral atom. Okay, so Na plus is smaller than Na due to the electrons being in a lower energy level, thus closer to the nucleus. Okay, and that will always work if the cation that we're discussing has lost enough electrons to take it back an energy level. So like in this case, of course, we went from level 3 to level 2. If that's the case, then that explanation will work every single time. But what about in a case like this, where we have a transition metal who has who can lose 1 electron, but who can also lose 2 electrons? In this case, it would be a discussion of who's bigger, who's smaller. That idea is no longer going to work, because if you think about the loss of the electrons here, it's a little bit harder to address in that situation. Although I guess you could do it thinking about the fact that takeaway point, transition metals always lose their s electrons first. But I'm kind of getting ahead of myself. The other reasoning that you can use would be this. So if I was talking about the copper plus 1 ion, so copper plus 1 has 29 protons in the nucleus, and the copper atom would have 29 electrons. However, if it's plus 1, it has 28 electrons, and if it's plus 2, it has 27 electrons. Okay, so the Zephs here are pretty much the same because we're talking about copper, and so really this is going to be more of a statement on the fact that copper plus 2 has fewer electrons that are repelling against each other. So I call those electron-electron repulsions. So fewer electron-electron repulsions due to a smaller number of electrons. Because there's fewer electron repulsions, the electrons are closer together, or can be closer together, resulting in a smaller atom. So that is kind of the second way to justify this idea. But the kind of bold statement is that cations are smaller than their neutral parent atom. Okay, so that's kind of your takeaway point for that. However, that idea doesn't exactly explain this copper plus 1 and copper plus 2. But so the other way to do it is to discuss that fewer electrons means fewer repulsions, and those electrons can be located closer to the nucleus. So if you take successive electrons, if you keep taking more electrons, that will result in even fewer electron repulsions, making your ions smaller. So we're kind of going to use the same philosophy in talking about anions. This time, of course, we're talking about gaining electrons. So this idea of a change in energy level really doesn't work, because if we think about F and F minus 1, that F's electrons are in the N equals 2 electron level, energy level, and so are F minus 1s. It's just that it's completed the energy level. So I haven't had a change in energy level here. I cannot use that for a justification on size. I also can't use Zeph for a justification on size, because F and F minus 1 have the same Zeph. So now all of a sudden we've encountered something interesting. We have equal energy levels and we have equal Zephs, which might make you think that these would be equal in size. But again, we're going to go back to this idea of electron repulsions. And if this was F, it has positive 9 protons in the nucleus, and F would have 9 electrons. F minus 1 would have 10 electrons. So in this case, F minus has more electron repulsions, causing those electrons to spread out or to move away from the nucleus, and this results in a larger size than the neutral atom. So kind of bold statement, anions are larger in size than their neutral parent atom. Okay, so cations are smaller, anions are larger, and it really deals with how many electrons there are and how the repulsion is happening. Okay, so that's your discussion on sizes of ions. And then we have this last thing to talk about, which we have mentioned before, about something called an isoelectronic series, which is a group of ions that have the same number of electrons and identical electron configurations. Okay, so a perfect example of an isoelectronic series would be O minus 2, F minus 1, Na plus 1, Mg plus 2. We could keep going. Aluminum plus 3. Okay, so the reason they fit this idea of isoelectronic is the fact that all of these species, or ions in this case, whether they're anions who have gained or cations who have lost, they all have 10 electrons. So that fits the first part of this definition, that they're a group of ions that have the same number of electrons. Okay, so check, they fit that criteria. They also must have identical electron configurations. And so in this case, they do, because they all have the configuration of neon, which is 1s2, 2s2, 2p6. So no matter how you play this game, you can think about oxygen, who's 1s2, 2s2, 2p4, but when it gains 2 electrons, it acquires the same configuration. You can also take it from a cation's perspective, something like sodium, whose configuration is 1s2, 2s2, 2p6, 3s1, but upon losing 1 electron, loses the 3s electron, and then also obtains neon's configuration. So technically speaking, to be isoelectronic, you have to meet 2 criteria. You have to have the same number of electrons, but you also have to have identical electron configurations. And we're going to see later where sometimes species can have the same number of electrons, but their electron configurations are different. Most of the time that results from discussing transition metals.